nations and cities are working to reduce their dependence on fossil fuels and promote sustainable energy options.
Because it's the smart thing, because it makes business sense, and it's the right thing.
In China, Europe, and Brazil, energy innovations are changing how we live. And in the U.S., every branch of the military is mobilizing to cut its carbon footprint.
We really believe that the climate is changing.
In this program, we'll share how we know Earth is warming and why, and discover what Earth science tells us about clean, green energy opportunities. I'm Richard Alley. I'm a geologist at Penn State University, but my research has taken me round the planet, from Greenland to Antarctica. I'm fascinated by how our climate has changed dramatically and often, from times with ice everywhere to no ice anywhere on the planet. Records of past climate help us learn how Earth operates. What has happened can happen again. And I know that sometimes things change really fast. I'm a registered Republican, play soccer on Saturdays, and go to church on Sundays. I'm a parent and a professor. I worry about jobs for my students and my daughter's future. I've been a proud member of the UN panel on climate change, and I know the risks. And I've worked for an oil company and know how much we all need energy. And the best science shows we'll be better off if we address the twin stories of climate change and energy, and that the sooner we move forward, the better. Our use of fossil fuels for energy is pushing us towards a climate unlike any seen in the history of civilization. But a growing population needs more and more clean energy. But I believe science offers us an operator's manual with answers to both of these huge challenges. Humans need energy. We always have and always will. But how we use energy is now critical for our survival. It all began with fire. Today, it's mostly fossil fuels. Now we're closing in on 7 billion of us, and the planet's population is headed toward 10 billion. Our cities and our civilization depend on vast amounts of energy. Fossil fuels, coal, oil, and natural gas, provide almost 80% of the energy used worldwide. Nuclear is a little less than 5%, hydropower a little under 6%, and the other renewables, solar, wind, and geothermal, about 1%, but growing fast. Wood and dung make up the rest. Using energy is helping many of us live better than ever before. Yet well over 1.5 billion are lagging behind without access to electricity or clean fuels. In recent years, Brazil has brought electricity to 10 million, but in rural Ceará, some still live off the grid. No electricity, no running water, and no refrigerators to keep food safe. Life's essentials come from their own hard labor. Education is compulsory, but studying's a challenge when evening arrives. The only light is from kerosene lamps. They're smoky, dim, and dangerous. Someday, this mother prays the electric grid will reach her home.
The first thing I'll do when the electricity arrives in my house will be to say a rosary and give praise to God.
More than half of China's 1.3 billion citizens live in the countryside. Many rural residents still use wood or coal for cooking and heating, although most of China is already on the grid. China has used energy to fuel the development that has brought more than 500 million out of poverty. In village homes, there are flat-screen TVs and air conditioners. By 2030, it's projected that 350 million Chinese, more than the population of the entire United States, will move from the countryside to cities, a trend that's echoed worldwide. Development in Asia, Africa, and South America will mean 3 billion people will start using more and more energy as they escape from poverty. Suppose we make the familiar, if old-fashioned, 100-watt light bulb our unit for comparing energy use. If you're off the grid, your share of your nation's energy will be just a few hundred watts, a few light bulbs. South Americans average about 13 bulbs. For fast-developing China, it's more like 22 bulbs. Europe and Russia, 5,000 watts, 50 bulbs. And North Americans, over 10,000 watts, more than 100 bulbs. Now, let's replace those light bulbs with the actual numbers. Population shown across the bottom, and energy use displayed vertically. Off the grid to the left, North America to the right. If everyone, everywhere, started using energy at the rate North Americans do, the world's energy consumption would more than quadruple. And using fossil fuels, that's clearly unsustainable. No doubt about it, coal, gas, and oil have brought huge benefits. But we're burning through them approximately 1 million times faster than nature saved them for us, and they will run out. What's even worse, the carbon dioxide from our energy system threatens to change the planet in ways that'll make our lives much harder. So why are fossil fuels such a powerful but ultimately problematic source of energy? Conditions on the waterways of today's Louisiana help us understand how fossil fuels are made and why they're ultimately unsustainable. Oil, coal, and natural gas are made from things, mostly plants, that lived and died long ago. It's taken hundreds of millions of years for nature to create enough of the special conditions that save the carbon and energy in plants to form the fossil fuels that we use. Here's how it works. Plants, like these tiny diatoms encased in silica shells, grow in the upper layers of lakes and oceans, using the sun's energy to turn carbon dioxide and water into more plants. When they die, if they're buried where there's little oxygen to break them down, their chemical bonds retain the energy that began as sunlight. If enough carbon-rich matter is buried deeply enough, for long enough, the Earth's heat and pressure turn it into fossil fuel, concentrating the energy that once fed the growing plants. Vary what goes into Earth's pressure cooker and the temperature, and you end up with the different kinds of fossil fuel. Woody plants make coal. Slimy plants, algae, will give you oil, and both of them give rise to natural gas. The fossil fuels formed over a few 100 million years, and we're burning them over a few 100 years. And if we keep doing that, sooner or later they must run out. But there's a bigger problem with fossil fuels. As we've seen, they're made of carbon primarily. When you burn them, you add oxygen, and that makes CO2 that goes in the air. We're reversing the process by which they formed. And if we keep doing this, it must change the composition of Earth's atmosphere. What CO2 does was confirmed by basic research that had absolutely nothing to do with climate change.
A continuance of the Upper Air program will provide scientific data concerning the physics of the upper atmosphere.
World War II was over, but the Cold War had begun. The U.S. Air Force needed to understand the atmosphere for communications and to design heat-seeking missiles. At certain wavelengths, carbon dioxide and water vapor block radiation. So the new missiles couldn't see very far if they used a wavelength that CO2 absorbs. Research at the Air Force Geophysics Laboratory in Hanscom, Massachusetts, produced an immense database with careful measurements of atmospheric gases. Further research by others applied and extended those discoveries, clearly showing the heat-trapping influence of CO2. The Air Force hadn't set out to study global warming, they just wanted their missiles to work. But physics is physics. The atmosphere doesn't care if you're studying it for warring or warming. Adding CO2 turns up the planet's thermostat. It works the other way as well. Remove CO2 and things cool down. These are the Southern Alps of New Zealand, and their climate history shows that the physicists really got it right. These deep, thick piles of frozen water are glaciers, slow-moving rivers of ice sitting on land. But once, when temperatures were warmer, they were liquid water stored in the sea. We're going to follow this one, the Franz Josef, from summit to ocean to see the real-world impact of changing levels of CO2. It's beautiful up here on the highest snowfield, but dangers lurk beneath the surface. I've spent a lot of time on the ice. It's standard practice up here to travel in pairs, roped up for safety. The glacier is fed by something like 6 meters of water a year, maybe 20 meters, 60 feet of snowfall, so really seriously high snowfall. The snow and ice spread under their own weight, and it's headed downhill at something like 1 kilometer a year. When ice is speeding up a lot as it flows towards the coast, it can crack and open great crevasses that give you a view into the guts of the glacier. Man, this is a big one. 10, 20, 30 meters more, 100 feet or more heading down in here, and we can see a whole lot of the structure of the glacier right here.
So what we're going to do is just go sit on the edge and then walk backwards and I'll lower you.
Tell me when. Okay, roll her around, and down we go. Snowfall arrives in layers, each storm putting one down. Summer sun heats the snow and makes it look a little bit different than the winter snow, and so you build up a history. In these layers, there's indications of climate, how much it snowed, what the temperature was. And all of this is being buried by more snow. And the weight of that snow squeezes what's beneath it and turns it to ice. And in doing that, it can trap bubbles. And in those bubbles are samples of old air, a record of the composition of the Earth's atmosphere, including how much CO2 was in it, a record of the temperature on the ice sheets, and how much it snowed.
Nice and slowly.
Okay.
So I'll pull on
As
this.
we'll see, we can open those icy bottles of ancient air and study the history of Earth's atmosphere. This landscape also tells the story of the ice ages and the forces that have shaped Earth's climate. Over the last millions of years, the brightness of the sun doesn't seem to have changed much. But the Earth's orbit and the tilt of its axis have shifted in regular patterns over tens and hundreds of thousands of years. The orbit changes shape, varying how close and far the Earth gets as it orbits the sun each year. Over 41,000 years, the tilt of Earth's axis gets larger and smaller, shifting some of the sunshine from the equator to the poles and back. And our planet has a slight wobble, like a child's top, altering which hemisphere is most directly pointed toward the sun when Earth is closest to it. Over tens of thousands of years, these natural variations shift sunlight around on the planet, and that influences climate. More than 20,000 years ago, decreasing amounts of sunshine in the Arctic allowed great ice sheets to grow across North America and Eurasia, reaching the modern sites of New York and Chicago. Sea level fell as water was locked up on land. Changing currents let the oceans absorb CO2 from the air. That cooled the southern hemisphere and unleashed the immense power of glaciers such as the Franz Josef, which advanced down this wide valley, filling it with deep, thick ice. Now, we're flying over today's coastline, where giant boulders are leftovers from that last ice age.
A glacier is a great earth-moving machine. It's a dump truck that carries rocks that fall on top of it. It's a bulldozer that pushes rocks in front of it, and it outlines itself with those rocks, making a deposit that we call a moraine that tells us where the glacier has been. We're 20 kilometers, 12 miles from the front of the Franz Josef Glacier today. But about 20,000 years ago, the ice was depositing these rocks as it flowed past us and out to sea.
The rocks we can still see today confirm where the glacier once was. Now, in a computer-generated time-lapse condensing thousands of years of Earth's history, we're seeing what happened. Lower CO2, colder temperatures, more snow and ice, and the Franz Josef advanced. 20,000 years ago, 30% of today's land area was covered by great ice sheets, which locked up so much water that the global sea level was almost 400 feet lower than today. Then, as Earth's orbit changed, temperatures and CO2 rose, and the glacier melted back. The orbits set the stage, but by themselves they weren't enough. We need the warming and cooling effects of rising and falling CO2 to explain the changes we know happened. Today, atmospheric CO2 is increasing still more, temperatures are rising, and glaciers and ice sheets are melting. You can see this clearly on the lake formed by the shrinking Tasman Glacier across the range from the Franz Josef.
This is what the end of an ice age looks like. Glaciers falling apart, new lakes, new land, icebergs coming off the front of the ice. In the early 1980s, we would have been inside New Zealand's Tasman Glacier right here. Now we're passing icebergs in a new lake from a glacier that has mostly fallen apart and ends over 6 kilometers, 4 miles away.
One glacier doesn't tell us what the world is doing, but while the Tasman has been retreating, the great majority of glaciers on the planet have gotten smaller. This is the Columbia Glacier in Alaska. It's a type of glacier that makes the effects of warming easy to see. It's been retreating so fast that the Extreme Ice Survey had to reposition their time-lapse cameras to follow its motion. In Iceland, warming air temperatures have made this glacier simply melt away, leaving streams and small lakes behind.
Thermometers in the air show warming. Thermometers in the air far from cities show warming. Put your thermometer in the ground, in the ocean, look down from satellites, they show warming. The evidence is clear. The Earth's climate is warming.
This frozen library, the National Ice Core Lab in Denver, Colorado, has ice from all over, kept at minus 35 degrees. The oldest core here goes back some 400,000 years. Here, really ancient ice from Greenland in the north and Antarctica in the south reveals Earth's climate history. Let's see what cores like this can tell us.
First are those layers I mentioned in the New Zealand snow. They've turned to ice and we can count them. Summer, winter, summer, winter. Like tree rings, we can date the core. Other cores tell other stories. Look at this. It's the ash of an Icelandic volcano that blew up to Greenland 50,000 years ago. Cores hold other and even more important secrets. Look at these bubbles. They formed as the snow turned to ice and trapped old air that's still in there.
Scientists now are working with cores from Antarctica that go back even further. They tell us with a very high degree of accuracy how much carbon dioxide was in the air that far back. Researchers break chunks of ice in vacuum chambers and carefully analyze the gases that come off. They're able to measure very precisely levels of carbon dioxide in that ancient air.
Looking at the cores, we see a pattern that repeats. 280 parts per million of CO2, then 180, 280, 180, 280.
By analyzing the chemistry of the oxygen atoms in the ice, you can also see the pattern of rising and falling temperature over time. Colder during the ice ages, warmer during the interglacial periods. Now put the two lines together and you can see how closely temperature and carbon dioxide track each other. They're not exactly alike. At times, the orbits caused a little temperature change before the feedback effects of CO2 joined in.
But just as we saw in New Zealand, we can't explain the large size of the changes in temperature without the effects of CO2. This is the signature of natural variation. The cycle of the ice age is driven by changes in Earth's orbit, with no human involvement.
But here's where we are today. In just 250 years, since the Industrial Revolution, we've blown past 380 with no sign of slowing down. It's a level not seen in more than 400,000 years, 40 times longer than the oldest human civilization. So physics and chemistry tell us that adding carbon dioxide to the atmosphere warms things up.
And Earth's climate history shows us there will be impacts, from melting ice sheets to rising sea level. But how do we know with equal certainty that it's not just more natural variation, that humans are the source of the increasing CO2?
When we look at a landscape like this one, we know immediately that volcanoes put out all sorts of interesting things, and that includes CO2.
So how do we know that the rise of CO2 in the atmosphere that we see comes from our burning of fossil fuels and not from something that the volcanoes have done? Well, the first step in the problem is just bookkeeping. We measure how much CO2 comes out of the volcanoes. We measure how much CO2 comes out of our smokestacks and tailpipes. The natural source is small. Humans are putting out 50 to 100 times more CO2 than the natural volcanic source. We can then ask the air whether our bookkeeping is right, and the air says that it is.
Volcanoes make CO2 by melting rocks to release the CO2. They don't burn, and they don't use oxygen. But burning fossil fuels does use oxygen when it makes CO2. We see that the rise in CO2 goes with a fall of oxygen, which says that the rising CO2 comes from burning something.
We can then ask the carbon in the rising CO2 where it came from.
Carbon comes in three flavors. The lightweight, carbon-12, which is especially common in plants. The medium weight, carbon-13, which is a little more common in the gases coming out of volcanoes. And the heavyweight, carbon-14. It's radioactive and decays almost entirely after about 50,000 years, which is why you won't find it in very old things like dinosaur bones or fossil fuels. We see a rise in carbon-12, which comes from plants. We don't see a rise of carbon-13, so the CO2 isn't coming from the volcanoes. And we don't see a rise in carbon-14, so the CO2 can't be coming from recently living plants. And so the atmosphere says that the rising CO2 comes from burning of plants that have been dead a long time.
That is fossil fuels. The CO2 is coming from our fossil fuels. It's us.
So physics and chemistry show us carbon dioxide is at levels never seen in human history. And the evidence says it's all of us burning fossil fuels that's driving the increase. But what about climate change and global warming? Are they for real? Here's what those who have looked at all the data say about the future.
Climate change, energy security, and economic stability are inextricably linked. Climate change will contribute to food and water scarcity, will increase the spread of disease, and may spur or exacerbate mass migration.
Who do you suppose said that? Not a pundit, not a politician, the Pentagon.
These war games at Fort Irwin, California provide realistic training to keep our soldiers safe. The purpose of the Pentagon's Quadrennial Defense Review, the QDR, is to keep the nation safe. The review covers military strategies for an uncertain world. The Pentagon has to think long-term and be ready for all contingencies. The 2010 QDR was the first time that those contingencies included climate change. Rear Admiral David Titley is oceanographer of the Navy and contributed to the Defense Review.
Well, I think the QDR really talks about climate change in terms that it really isn't for debate. And you take a look at the global temperatures, you take a look at sea level rise, you take a look at what the glaciers are doing, not just one or two glaciers, but really glaciers worldwide. And you add all of those up together. And that's one of the reasons we really believe that the climate is changing. So the observations tell us that. Physics tells us this as well.
What climate change means for key global hotspots is less clear.
We understand the Earth is getting warmer. We understand the oceans are getting warmer. What we do not understand is exactly how that will affect things like strong storms, rainfall rates, rainfall distribution. So yes, climate change is a certainty, but what is it going to be like in specific regions of the world and when?
One area of particular concern to the Navy is sea level rise.
Sea level rise is going to be a long-term and very, very significant issue for the 21st century.
The QDR included an infrastructure vulnerability assessment that found that 153 naval installations are at significant risk from climatic stresses. From Pearl Harbor, Hawaii to Norfolk, Virginia, the bases and their nearby communities will have to adapt.
Even with 1 to 2 meters of sea level rise, which is very, very substantial, we have time. This is not a crisis, but it is certainly going to be a strategic challenge.
Globally, climate change is expected to mean more fires, floods, and famine. Nations may be destabilized. For the Pentagon, climate change is a threat multiplier. But with sound climate science, Titley believes forewarned is forearmed.
The good thing is the science is advanced enough in oceanography, glaciology, meteorology, that we have some skill at some time frames of predicting this. And if we choose to use those projections, we can, in fact, by our behavior, alter the future in our favor.
Titley and the Pentagon think the facts are in.
Climate change is happening, and there is very, very strong evidence that a large part of this is, in fact, man-made.
Aid with some of the cows you've got.
The military is America's single largest user of energy, and it recognizes that its use of fossil fuels has to change. The Pentagon uses 300,000 barrels of oil each day. That's more than 12 million gallons. An armored Humvee gets 4 miles to the gallon. At full speed, an Abrams battle tank uses 4 gallons to the mile. And it can cost as much as $400 a gallon to get gas to some remote bases in Afghanistan. Fort Irwin is a test bed to see if the Army can operate just as effectively while using less fossil fuel and more renewables. And it's not just Fort Irwin and the Army. At Camp Pendleton, Marines were trained on an energy-saving, experimental forward operating base that deployed with them to Afghanistan.
Before any equipment goes into theater, we want Marines to get trained on it. So what are some of the things that we could take hold of right away and make sure that we can make a difference for the warfighter downrange?
They test out different kinds of portable solar power units. They also practice how to purify stagnant water and make it drinkable. The Army and Marines both want to minimize the number of convoys trucking in fuel and water. A report for the Army found that in 5 years, more than 3,000 service members had been killed or wounded in supply convoys.
And if you've got Marines guarding that convoy, and God forbid it get hit by an IED, then what are the wounded, what are the deaths involved in that, and really, are we really utilizing those Marines and that capability the way we should?
Generators used to keep accommodations livable and computers running are also major gas guzzlers.
Right now what we're doing is putting up a power shade. It has flexible solar panels on the top and gives us enough power to run small electronics such as lighting systems and laptop computers. It also provides shade over the tent structure. Experimenting with this equipment in Africa proved that it could reduce the internal temperature of the tent 7 to 10 degrees. Plug them in.
All the LED lights in the entire tent use just 91 watts, less than one single old-fashioned incandescent bulb.
It's a no-brainer when it comes to efficiency.
Light-emitting diodes don't weigh much, but they're still rugged enough to survive a typical Marine's gentle touch.
When we put something into a military application and they beat it up, it's ruggedized. It's ready for the worst that the world can take. And so one thing that people say is if the military has used this thing and they trust it, then maybe it's okay for my backyard.
Renewable energy will also play an important role at sea and in the air. The Navy's Macon Island is an amphibious assault ship with jump jets, helicopters, and landing craft. It's the first vessel to have both gas turbines and a hybrid electric drive, which it can use for 75% of its time at sea. This Prius of the ocean cut fuel costs by $2 million on its maiden voyage. By 2016, the Navy plans to have what it calls a Great Green Fleet, a complete carrier group running on renewable fuels with nuclear ships, hybrid electric surface vessels, and aircraft flying only biofuels. By 2020, the goal is to cut usage of fossil fuels by 50%. Once deployed in Afghanistan, the XFOB cut down on gas used in generators by over 80%. In the past, the Pentagon's innovations in computers, GPS, and radar have spun off into civilian life. In the future, the military's use of renewable energy can reduce dependence on foreign oil, increase operational security, and save lives and money.
A lot of the times it is a culture change more than anything else. And the Department of Defense over the years has proved time and time again that it can lead the way in that culture change.
If the U.S. military is the largest user of energy in America, China is now the largest consumer on the planet. At 1.3 billion, China has a population about 4 times larger than the U.S. So average per person use and CO2 emissions remain about 1/4 those of Americans. But like the U.S. military, China is moving ahead full speed on multiple different sustainable energy options. And it pretty much has to. Cities are congested, the air is polluted, continued rapid growth using old technologies seems unsustainable.
I come 3. Yes.
This meeting in Beijing brought together mayors from all over China, executives from state-owned enterprises, and international representatives. The organizer was a U.S.-Chinese NGO headed by Peggy Liu.
Over 20 years, we're going to have 350 million people moving into cities in China. And we're going to be building 50,000 new skyscrapers, the equivalent of 10 Manhattans, 170 new mass transit systems. I mean, it's just incredible, incredible scale.
This massive, rapid growth comes with a high environmental cost.
They recognize that they're spending as much as 6% of their gross domestic product on environmental issues.
In 2009, China committed $35 billion, almost twice as much as the U.S., to energy research and incentives for wind, solar, and other clean energy technologies. It's attracted an American company to set up the world's most advanced solar power research plant. China now makes more solar panels than any other nation. But it's also promoting low-tech, low-cost solutions. Solar water heaters are seen on modest village homes. Some cities have them on almost every roof.
China is throwing spaghetti on the wall right now in terms of over 27 different cities doing LED street lighting, or over 20, 30 different cities doing electric vehicles.
But visit any city and you can see that the coal used to generate more than 70% of China's electricity has serious consequences with visible pollution and adverse health effects. China uses more coal than any other nation on Earth, but it's also trying to find ways to burn coal more cleanly.
In 3 years, 2006 to 2009, while China was building one new coal-fired power plant a week, it also shut down inefficient coal plants. So, it's out with the old and in with the new, and they're really trying hard to invent new models.
This pilot plant, designed for carbon capture and sequestration, was rushed to completion in time for Shanghai's 2010 World Expo. It absorbs and sells carbon dioxide and will soon scale up to capture 3 million tons a year that could be pumped back into the ground, keeping it out of the air.
Here in China, they are bringing many plants online in a much shorter time span than it takes us in the U.S.
China is right now the factory of the world. What we'd like to do is turn it into the clean tech laboratory of the world.
If nations choose to pay the price, burning coal with carbon capture can offer the world a temporary bridge until renewables come to scale.
China's going to come up with the clean energy solutions that are cost-effective and can be deployed at large scale. In other words, solutions that everybody around the world wants.
Can low-carbon solutions really give us enough energy to power the planet and a growing population? Let's put some numbers on how much energy we can get from non-fossil fuel renewables. Today, all humans everywhere on Earth use about 15.7 terawatts of energy. That's a big number. In watts, that's 157 followed by 11 zeros. Or 157 billion of those 100-watt light bulbs we used as a reference. To show what's possible, let's see if we can get to 15.7 terawatts using only renewable energy. I'm here in the Algodones Dunes near Yuma, Arizona. The Guinness Book of Records says it's the sunniest place in the world. There's barely a cloud in the daytime sky for roughly 90% of the year.
0.01%. 1/100th of 1%. If we could collect that much of the sun's energy reaching the Earth, it would be more than all human use today.
Today's technologies have made a start. This was the world's first commercial power station to use a tower to harvest concentrated solar energy. Near Seville, Spain, 624 mirrors stretch over an area of more than 135 acres, beaming back sunlight to a tower nearly 400 feet high. Intense heat produces steam that drives a turbine, which generates electricity. When completed, this one facility will be able to power 200,000 homes, enough to supply the entire nearby city of Seville. Remember our target of 15.7 terawatts? Well, the sun delivers 173,000 terawatts to the top of Earth's atmosphere, 11,000 times current human use. No way we can capture all of that potential energy at Earth's surface, but the deserts of America's Southwest, with today's technology, have enough suitable land to supply 80% of the entire planet's current use. Of course, there's one big problem with solar power: night. But with more efficient transmission lines, and as part of a balanced renewable energy portfolio that includes storage, the sun's potential is vast. In tropical nations like Brazil, the sun heats water, makes clouds, and unleashes rainfall that feeds some of the planet's largest rivers. Iguazu Falls is a tourist attraction, one of the most spectacular waterfalls on Earth, where you can feel the immense power of falling water. The nearby Itaipu Dam, on the border of Brazil and Paraguay, produces the most hydroelectric power of any generating station in the world. This one dam supplies most of the electricity used in Sao Paulo, a city of more than 11 million. Sao Paulo is 600 miles away, but Brazil made the decision to build innovative, high-voltage direct current transmission lines to minimize energy loss. The Itaipu to Sao Paulo electrical grid has been in operation since 1984 and shows that renewable energy can go the distance. Dams can't be the answer for every nation. They flood landscapes, disrupt ecosystems, and displace people. But hydropower gives Brazil, a nation larger than the continental United States, 80% of its electricity. And worldwide, hydropower could contribute 12% of human energy use, ready at a moment's notice in case the sun goes behind a cloud. Brazil is also using its unique natural environment in another way. Its tropical climate provides ideal conditions for sugarcane, one of the Earth's most efficient plants in its ability to collect the energy of sunlight. Plantations like this one harvest the cane for the production of sugar and the biofuel called ethanol. The U.S. is actually the #1 producer of ethanol in the world, mostly using corn instead of cane. But ethanol made from sugarcane is several times more efficient at replacing fossil fuel than corn-based ethanol. Modern facilities like this one pipe back wet waste to fertilize the fields and burn the dry waste, called bagasse, to generate electricity to run the factory. For Brazil, at least, ethanol works. Today, almost all cars sold in Brazil can use flex fuels. Drivers choose gasoline blended with 25% ethanol or pure ethanol, depending on price and how far they plan to drive. Local researchers say that if all the gasoline in the world suddenly disappeared, Brazil is the only nation that could go it alone and keep its cars running. Using food for fuel raises big questions in a hungry world. As of now, sugarcane ethanol hasn't affected food prices much. But there are concerns with corn. So here in the US, government labs like NREL, the National Renewable Energy Lab, have launched programs to see if biofuels can be made from agricultural waste. It does work, and researchers are trying to bring the cost down. So with plants capturing roughly 11 times human energy use, they're a growing opportunity. New Zealand takes advantage of another kind of energy. These are the geysers and hot springs at Rotorua on the North Island. Once, they were used by the native Maori people for cooking and bathing. Now, geothermal power plants harvest heat and turn it into as much as 10% of all New Zealand's electricity. Many power projects are partnerships with the Maori, benefiting local people and avoiding the not in my backyard problems that often complicate energy developments. Globally, geothermal energy offers 3 times our current use. But we can mine geothermal, extracting the energy faster than nature supplies it, cooling the rocks deep beneath us to make power for people. This energy exists even where you don't see geysers and mud pots, so it can be extracted without harming these natural wonders. A study by MIT showed that the accessible hot rocks beneath the United States contain enough energy to run the country for 130,000 years. And like hydroelectric, geothermal can provide peaking power, ready to go at a moment's notice if the sun doesn't shine and the wind doesn't blow. Mining energy from deep, hot rocks is a relatively new technology, but people have been using windmills for centuries. And the wind blows everywhere. Here's where the United States is very lucky. Let's take a trip up the nation's wind corridor, from Texas in the south to the Canadian border. Bright purple indicates the strongest winds. All along this nearly 2,000 miles, there's the potential to turn a free, non-CO2 emitting resource into electricity. But that takes choices and actions by individuals and governments. Here's what's been happening in West Texas. It's a land of ranches and farms and, of course, oil rigs and pump jacks. But in the early 90s, this was one of the most financially depressed areas in the state. Communities like Nolan Divide fell on hard times. Schools closed, people moved away. But since 1999, the new structures towering above the flat fields aren't oil derricks, but wind turbines. The largest number, more than 1,600, is in Nolan County. Greg Wortham is mayor of Sweetwater, the county seat.
It wasn't a philosophical or political decision. It was ranchers and farmers and truck drivers and welders and railroads, and wind workers.
Steve Oatman's family has been ranching the Double Heart for 3 generations. Steve may have doubts about the causes of climate change, but not about wind energy.
But it's been a blessing. It helps pay taxes, it helps pay the feed bill. Roscoe 30 meg.
We talk about this being green energy because it pays money. The ranchers and the farmers call it mailbox money. They have to get out and sweat and work hard all day long. Things are pretty stressful. And if you can just walk to the mailbox and pick up some money because you've got turbines above the ground, that makes life a lot easier.
Each windmill can generate between $5,000 and $15,000 per year. So a ranch with an average of 10 to 20 turbines can provide financial stability for people who have always lived with uncertainty.
I don't just believe in it because I make a living from it. It's something that's going to happen for the country.
So now, local schools have growing enrollments and funds to pay for programs.
We had about $500 million in tax base in the whole county in 2000, and by the late part of that decade, in less than 10 years, it went up to $2.5 billion in tax value.
By the end of 2009, the capacity of wind turbines in West Texas totaled close to 10,000 megawatts. If Texas were a country, it would rank 6th in the world in wind power. The U.S. Department of Energy estimates that wind could supply 20% of America's electricity by 2030. New offshore wind farms would generate more than 43,000 new jobs. That translates into a $200 billion boost to the U.S. economy. Worldwide, wind could provide almost 80 times current human usage. No form of energy is totally free of environmental concerns or hefty startup costs. Some early wind farms gave little consideration to birds and other flying critters like migrating bats. But recent reports by Greenpeace and the Audubon Society have found that properly sited and operated turbines can minimize problems. Mayor Wortham, for one, welcomes wind turbines into his backyard.
We like them. Some people don't. But we're more than happy to export our energy to those states who want to buy green but don't want to see green.
In the long run, I hope we have wind turbines everywhere they can produce energy. We need them. That's what America's going to have to do. That's the next stepping stone to save ourselves.
The state of Texas has invested $5 billion to connect West Texas wind to big cities like Dallas and Fort Worth. Farther south is Houston, one of the most energy-hungry cities in the country. Its port is America's largest by foreign tonnage, and its refineries and chemical plants supply a good portion of the nation. But already, perhaps surprisingly, Houston is the largest municipal purchaser of renewable energy in the nation. 30% of the power city government uses comes from wind, with a target of 50%. And its mayor wants to cut energy costs and increase energy efficiency.
I want to go from the oil and gas capital of the world to the green and renewable energy capital of the world.
Supported by federal stimulus dollars, the local utility is ahead of schedule to install smart meters. These will help consumers economize on energy use. The city has already installed 2,500 LED traffic lights using 85% less energy than traditional incandescent bulbs. That translates into savings of $3.6 million per year. City Hall thinks it can also improve air quality by changing the kinds of cars Houstonians drive.
If we're going to be a car city, that's great, but those vehicles are going to be non-polluting electric vehicles.
The city already operates a fleet of plug-in hybrids. Now it's encouraging the development of an infrastructure to make driving electric vehicles easy and practical. And in Houston's hot and humid environment, it helps to have an increasing number of energy-efficient LEED-certified buildings.
We're going to do it because it's the smart thing, because it makes business sense, and it's the right thing.
Some estimates are that the U.S. could save as much as 23% of projected demand from a more efficient use of energy.
Well, if you're going to tackle energy efficiency, you might as well do it in a place that is a profligate user of energy. And when you make a difference there, you can make a difference that's significant.
Globally, efficiency could cut the demand for energy by 1/3 by 2030. Bottom line, there are many ways forward, and we can hit that renewable energy target. And if next-generation nuclear is also included, one plan has the possible 2030 energy mix transformed from one relying on fossil fuels to one that looks like this. With renewables, sun, wind, geothermal, biomass, and hydropower totaling 61%. Fossil fuels down to 13%, and existing and new nuclear making up the balance. Another plan meets world energy needs with only wind, water, and solar. And in fact, there are many feasible paths to a sustainable energy future. Today's technologies can get us started, and a commitment to research and innovation will bring even more possibilities. We've traveled the world to see some of the sources the planet offers to meet our growing need for clean energy. There's too many options to cover all of them here. And besides, each nation, each state, each person must make their own choices as to what works best for them. But the central idea is clear. If we approach Earth as if we have an operator's manual that tells us how to keep the planet humming along at peak performance, we can do this. We can avoid climate catastrophes, improve energy security, and make millions of good jobs. For Earth, the Operator's Manual, I'm Richard Alley.
For the annotated illustrated script, with links to information on climate change and sustainable energy, web-exclusive videos, educator resources, and much more, visit pbs.org. Earth, the Operator's Manual is available on DVD. The companion book is also available. To order, visit shoppbs.org or call us at 1-800-PLAY-PBS. When the settlers first came to America, the forests were so thick that you could barely see the sky. But a growing population cleared land for farming and burned wood to make charcoal. Soon, the East Coast forests disappeared. But it's possible to use trees sustainably. In Brazil, in a town named Carbanita, a local cooperative harvests fast-growing eucalyptus to feed their charcoal furnaces. Close by, an international steelmaker plants vast areas of trees. One Brazilian environmentalist claims his nation's entire steel industry could offset all manufacturing emissions by growing eucalyptus to capture carbon dioxide. If we marry lessons from the past to practices designed for a sustainable future, Earth's forests and our planet can survive and thrive. Almost 2,000 years ago, the first emperor of China created an army of terracotta warriors to guard him in the afterlife. The bodies were mass-produced, but skilled craftsmen gave the faces personality. Today, it's wind turbines and solar panels that are being mass-produced to protect the environment, while the warriors remain a wonder of the world. In this century, China will create new wonders to help Red China turn green. We're used to looking at Earth from space. and marveling at its beauty. But we need to understand the natural forces that shape our planet to protect that beauty from the effects of how we use energy. As the sun warms Earth, it sets air into motion. And we've begun to harvest the wind. In turn, the wind delivers energy we can capture. Tides sweep in, and new machines are being built to harness their daily ebb and flow. Add up all the sustainable resources the planet offers, deploy all the ingenuity our species can summon, and we can more than meet our need for energy. If we look at our planet with eyes informed by science, and with the respect its beauty demands, and with the insights of an operator's manual. Beyond broadcast, Earth the Operator's Manual also includes outreach events at the North Carolina Museum of Natural Sciences, the Fort Worth Museum of Science and History, the Reuben H. Fleet Science Center in San Diego, the Science Museum of Minnesota, and the Oregon Museum of Science and Industry. Science centers have the latest information about climate science and sustainable energy. Visit them in person or online via Earth the Operator's Manual at pbs.org.